I'll be talking about tensor networks, which is a topic that I work primarily on. And I use them at CCQ to apply them to quantum systems, but also I have a side interest in applying them in the area of machine learning, and I'll tell you about those applications too. And the overview of the talk will be first just some basic background on tensors. So that's a good place. I'll go kind of quickly there. So that's a good place to ask me some questions if you have them, or if you want to, complain about, some things I say about tensors, that's welcome too. And then I'll go through one perspective on like how tensor networks arise, which is a perspective. This is the most technical part of the talk. I'll talk about how you can view tensor networks as a generalization of matrix factorizations, low rank factorizations to the case of tensors, but we'll take some other perspectives too. Then I'll go quickly through some different applications of tensor networks. And one of the goals of the talk, one of the main goals, if you don't take anything else away, is that I think now it's really clear that tensor networks have definitely moved outside of quantum physics applications, and in the last 10 years are really broadening their reach to all kinds of things, and they may be touching on the topics that you work on. So I'd really like to talk to you about how maybe we could, share knowledge or collaborate or something like that. Or at least I could get you started or pointed in the right direction. And then I'll briefly talk about the iTensor software, which we develop at CCQ to work with tensor networks. And if there's time in the discussion, I have like a little demo I can share with everybody about using iTensor for one of the applications that I'll mention. So for that part, if you have time, if you have Julia on your computer already, great. If not, it's easy to install. You can just go to julialang.org. And then there's a downloads link. You could go to this link, or you can just go to Julia Lang. And then there's a very clear download button there. Then, while I'm talking, if you are interested in doing this demo later, after that, go to the iTensor website, and it has a complete set of instructions. It's right on the front page, but this is a screenshot of the more detailed installation page. And even though it looks like a lot of steps, it's actually very simple. You just run the Julia command line program. That's called the REPL in Julia. And then you just hit the right bracket button, which goes into the package manager mode automatically. Then you just type add iTensors, and then you just wait, and it takes about a minute to install. So that installs the iTensor software. That's all you have to do. Okay, so I have to turn away from this slide, but all of this is on itensor.org. So it's right on the front page. If you just go there and scroll about halfway down, you'll see these instructions. All right, so now let's start with the introduction to tensors, just a very basic introduction. What is a tensor and where do tensors occur? Just a few contexts where they come up. So what is a tensor? Now, a few of you, I'm just preparing you, may bristle at this slide, but I'll address this in a couple of slides. For the purpose of this talk, a tensor is a multidimensional array. That's what I mean by a tensor. And so in that sense, you can view it as a generalization of a vector or a matrix, or a scalar even. So you can think of a scalar as a 0-order tensor, a vector as an order 1 tensor, matrix as an order 2 tensor. So then naturally you could keep going. If a matrix is like an array of numbers, then you can have a 3rd-order tensor, which is a 3D array of numbers. And then you can have a collection of these, which would be a 4th-order tensor, and so on. And we'll see in a minute that you can see that this gets very hard to draw around order 4, even 3. So we'll see in a minute that there's a nicer way to draw these, which is mathematically useful, called tensor diagrams. Now, really the modern definition of a tensor is actually a multilinear function of vectors. And this is not too hard to understand. You just think of a function that eats some number of vectors coming from some size of vector space. So, just think of these as columns of numbers that you can plug into this function called t. And then what makes t a tensor is that it's multilinear. So in each of its arguments, if I put in a linear combination of 2 vectors, ax1 plus bx2, then I can distribute t over that linear combination and pull the coefficients out. And that's true of all 4 of the slots. Then this is a tensor. So it's a function that eats some number of vectors. And so in this case, it eats 4. So this is an order 4 tensor. In general, you can talk about order n tensors. So that's really what a tensor is. And this is a more geometrical basis independent way of talking about them. So how does that connect back to this multidimensional array picture? Well, the way it connects back is that, so let's take a concrete example of one that we know. Let's take an order 2 tensor. So this is a function that's multilinear that eats 2 vectors. So the way you get back to this multidimensional array picture is you just imagine, or you just plug in all the standard basis vectors into the 2 slots. So standard basis vectors meaning vectors that are all 0 except for a 1 in the jth slot. You just plug those in. every different combination in, and whatever number comes out fills out a matrix, a two-dimensional array. And then the key point is that because the function's multilinear, I can make any v or w out of these ei and ej, some linear combination of those. And then I know immediately how m will act on a v and a w through these coefficients, because I can make v and w out of ei and ej. So everything about how m acts on any vectors is already determined by these coefficients because of the multilinear property. So really, this is all the information that defines this tensor. And so it is correct to say that a tensor is a multidimensional array as long as you know what basis you're in. So as long as there's some understanding of a standard basis that you're talking about. And in many applications, like in physics in particular, we know what basis we're in. So when we're doing quantum computing, there's a given basis of qubits that we start in and we work in the entire time. So we know what these arrays mean in those contexts. Okay, so a good chance to ask a question there if you need any more background on tensors. So basically a multidimensional array, but there's some mathematical pedigree as well. It has to do with, there's some things you can say about transformations, but they won't really be relevant for this talk too much. Okay, so now where do tensors occur? They occur in lots of places, and we'll see many more applications later in the talk. But some simple ones are that there's a whole activity in machine learning of thinking of data in a tensorized form. So rather than thinking of data just as a linear array of numbers, you can think of some types of data more naturally as tensors and get some advantages from doing this. So you can think of image data as being stored in order 3 tensors, where you have one index that's the x coordinate of pixels, a y coordinate of pixels index, and a third index that would go over RGB values or other values. Or you could have more heterogeneous data like medical data or tabular data, and then then it's more naturally fit into a tensor because each index goes over some different, like if you think of a spreadsheet or something, it's like a different axis of a multidimensional spreadsheet that you might have. And thinking about data this way isn't just sort of a way to be fancy, but this is actually something that can lead to advantages because you can apply sophisticated tensor factorization techniques, of which tensor networks are an example, to reveal structure in the data or to infill missing data or other kinds of interesting things that you can do. Another different way that tensors arise is working with functions. So things like approximating functions, integrating high dimensional functions, which we'll talk about a bit later. And in those cases, to put it on a computer, you need to discretize it in some way. There's different ways, of course. One of the simplest ways is just to use a grid. And if you do that, you just define a set of grid points. So here A is like some kind of grid spacing, like a uniform grid spacing. And N just indexes where you are in the grid. And that defines inputs xn. And then you can plug all these inputs into the different slots of the function, and that defines a tensor. So even though the function is not at all a linear thing, you can still pull a multidimensional array out of it. And then you can think of that in a much higher dimensional space, and you can do linear transformations on it to decompose it or study its structure. So you can still linearize the problem, but you pay a cost of going to a higher dimensional space. But then tensor networks give you ways of doing that efficiently. And I just wanted to note, this is one of the primary ways that tensors come up in quantum physics. So if you're wondering what we're doing at CCQ upstairs, this is a lot of what we're doing is our function f is this probability distribution of a bunch of quantum particles moving around in 3D. And we're trying to represent and store that and then solve it in some kind of partial differential equation and do things like that. So we use this idea a lot implicitly. Now, there's a really big problem, though, with these proposals of using big tensors with lots of indices. So the biggest problem is this thing called the curse of dimensionality. And the problem here is that if you go from order 2 tensors to order 3 tensors, here I'm showing an order 6 tensor with 6 indices. In general, an order n tensor, so like at CCQ, we want to take n basically to infinity, then the number of entries in the tensor grows exponentially. And that's easy to see if you just count. You have 10 values for n1, 10 values for n2. I'm just taking 10 arbitrarily, 10, 10, 10. So then you get 10 to the 6 entries in general that could be inside this array. And if you have n indices, you could have 10 to the n entries. So it's just growing out of control very, very fast. So that's a problem. So if you ever have an idea and you say, let's work with an order n tensor, you're just dead in the water as soon as you do that without some kind of approximation scheme. Another milder problem too in thinking about higher order tensors is that they're hard to notate and visualize. So if you use this kind of way of thinking about them as these multidimensional arrays and you try to draw them, it's very unwieldy to actually try to draw them and try to orient yourself about where the entries are. And then if you try to draw expressions about combinations of tensors, like contracting different tensors together, and here's an example of an expression you'll actually encounter in some literature. I'm not asking you to understand this expression right now, although this is a tensor network, but you actually see expressions like this in a lot of papers. It's difficult to understand unless you've seen that exact expression before. There's a lot of indices flying everywhere, and it's very difficult to see what's going on. And that's kind of tied to these other problems of notating tensors. So traditional index notation starts to really not be up to the task. So fortunately, there's a way out thanks to this year's one of this year's Nobel Prize winners, Roger Penrose, who devised this really nice notation called tensor diagram notation, which I'll use basically exclusively the rest of the talk. So let me make sure you are up to speed on that notation. So this notation, it looks like it's drawings like schematics, but they're actually rigorous notation of mathematical objects and sums. The way it works is that if you have a tensor with n indices, you draw it as some kind of shape, and the orientation of the shape and the shape of the shape is not the most important thing. You can kind of use some conventions there, but basically there's no hard and fast rules. The only hard and fast rule I'll tell you on the next slide, but the lines coming out notate the indices. And then, so, you can see some examples like low order examples, like a vector would be a shape with one line coming out, a matrix would be a shape with two lines coming out. Here's an order 3 tensor. So it's much easier to draw a higher order tensor. You just have more lines coming out. So you don't get into the business of having to draw in 3D. You just put more lines coming out of the object. The other advantage is that instead of having to notate sums over combinations of tensors, sums of products of tensors this way, and come up with names for everything, you just connect the lines, and you don't even have to put names most of the time or on most of the lines. So the idea is that here's a traditional expression where we have an index j summed over with another copy of this index j, and we have to put a big summation symbol. And sometimes you'll see people draw lines to help find pairs of indices that are summed over. So the idea here is that this line becomes the whole notation. So this line becomes this line. And you can put this letter if you want, but you don't have to. So then any index lines that match are summed over. And so this is really a drawing of a sum. It's a notation for a sum. And here's a sum where you have two matrices, because we can see there's two lines coming out of each object. And both indices are summed over, and we can immediately see the results as scalar because there's no indices left over. We can even see properties like that if I take this blue one and I slide it around the back of the ring, the answer won't change. And sure enough, this is the trace of a product of two matrices. And we just proved that it's cyclically permutation invariant just by visual inspection. So it's a nice notation. And as I was saying, when you have really complicated expressions like this, they're much clearer in diagram notation. So this big tensor becomes this shape with lines, and this kind of horrible looking sum just becomes this really elegant chain of tensors that are all linked together by a single index each, with these lines sticking out. And these are these n indices here on the top. So it's just a lot easier to see what's going on and to kind of orient yourself. But it's equally rigorous to traditional notation. Okay, and then just to kind of hint about later about iTensor, the idea of iTensor is that you ought to be able just to stare at these drawings and write code rather than having to get into the business of sort of knowing which index is in what ordering on your tensors. That's the philosophy. Okay. So now let's go to tensor networks. How are we going to actually work with, how are we going to try to break the curse of dimensionality and work with really large tensors in a practical way? So the curse of dimensionality, as I was saying, is the problem that we can't store or manipulate a tensor that has n indices for n too large. So maybe for n of 8 we can do it, 10 is okay. But once you get to n of 40, even if the index dimensions are 2, you're really toast. It doesn't work out. So you don't have any options just to store a whole tensor. And there's various ways around this problem. So one that's under very heavy investigation in the math literature is using various kinds of sparsity. So if you know or only have some of the entries of your tensor, or if you know most of them are 0, then there's a lot you can do. And there's a very, very interesting literature about this, but that's not what I'll be talking about today. So that's a very important case. Another way around.
Sorry, can I interrupt you for just 1 second?
Sure.
Sorry.
Uh-huh.
So with this notation, I understand how you would denote the trace, but how do you denote the diagonal of a matrix or a tensor?
Yeah, that's a good question. There are some weaknesses of the notation, like some things become a little hard to notate, but that one, what's commonly done is that you introduce special tensors like a kind of a multi-dimensional Kronecker delta tensor, or you can call it a copy tensor. And it's usually denoted with a small black dot. with a bunch of lines coming out of it. And then you just basically take the indices that you want to lock together and you connect them all to this Kronecker delta tensor with one other index coming out. So you basically introduce like a helper tensor to take the diagonal.
Okay, cool. Thank you.
Mm-hmm.
Is there a...
But you are touching on something important. Some things are awkward to notate in the diagram notation, though. Yeah.
Perhaps a related question. Is there a notation for covariant or contravariant indices?
Yes, great question. So the notation for that is arrows. You put arrows on the indices. And so usually what I do is an out arrow is a contravariant index and an in arrow is a covariant.
Thank you.
Mm-hmm. But the arrows aren't put if that's not playing a very important role in the calculation. So it's sort of an optional thing. Okay, great. Yeah, those are some good questions. So now other ways out that I was mentioning, one that I'm not trying to be too rigorous about, but is you can use sampling. So you can say, let's not try to store this whole tensor, but let's think of it as a function on these discrete values and only access some of the values and just work with the collection of samples that we got. But the one that I'll be focusing on that leads to the idea of tensor networks is the idea of low rank structure. And many of you are experts in low rank structures and you know all about the SVD and this kind of thing, but I'll run back through those concepts in the next slides just to make sure everybody can keep up with that if you're not familiar with those things. So let's just go to the simplest case when talking about low rank. Unfortunately, I'll have to go through this kind of quickly, but this is just some background on low rank. And let's talk about a low rank matrix and what's one way of uncovering the rank of a matrix. So one way to do this is to use the SVD. And the SVD is a very elegant decomposition. One nice thing about it is that it always succeeds. You can take any matrix you want and compute its SVD, singular value decomposition. So let's take some matrix M, compute its SVD. And what that does is it gives us a matrix U, a diagonal matrix S, and another matrix V. And then we can just collect this into two matrices by taking the square root of S and putting it into U and putting it into V. We can get matrices A and B. And the idea is that what we'll find is that in some cases, S will not be as large as it could be. It will have zeros in the diagonal, and so we can just truncate those away. And we'll find that this new index between A and B runs over a smaller number of values R, and that's the rank of M. So M, if it was some kind of 100 by 100 matrix, this index here may only be of size 4 or something like that. So it'd be a rank 4 matrix, even though it's in a 100 by 100 space. I probably said some things wrong mathematically there, but I think you know the idea. So now let's actually see an example of an SVD of a matrix, just to be really concrete about it. So let's take a particular 4 by 3 matrix M. And those of you who know about low rank matrices could already probably see that there's something low rank about this matrix. There's clearly some structure. We can see repeated numbers and things like that. But we don't know for sure, but the SVD will tell us. So we compute the SVD and we find that we get these matrices. We get this matrix U, we get S, and we get V. And let's look at these matrices and their properties. So the idea is that U is a partial isometry. If it's square, it's a unitary. So it has the property that U dagger U is 1. And V is like that too. V dagger V is the identity as well. What's most interesting is the matrix S. These are the singular values running down the diagonal of S. S is always diagonal with real entries that are non-negative and decreasing, or can always be taken to be decreasing. And so that's already pretty remarkable. So that's true no matter how singular M might be, or whether it's complex or anything like that. And what's really nice about this is that you can devise a controlled approximation for M by discarding small singular values. So you go from the bottom of the diagonal of S, and then you start discarding the singular values one by one, starting from the smallest ones. And I'll show you the matrix that results as you do this. And I'll show you the difference from that matrix to the original one, the distance. So throw away the smallest singular value and you make an error, and it turns out to be the square of the smallest singular value. And then throw away the next one, and that turns out to be the sum of squares of the singular values that you've thrown away. So you get an approximation, and you get to know how well you're doing as you're throwing these away. It tells you the SVD sort of tells you the error that you're making as you compress the matrix more and more. Because once you throw away these singular values, meaning set them to 0, you can get rid of the associated rows and columns of S, but most importantly, associated rows and columns, columns of U and rows of V. So that's the idea. So we can shrink these matrices down and save memory and save computational time. So if this is a bit circular, but if M is approximately low rank, then truncating singular values of the SVD gives an optimal approximation, optimal under various norms. There's more than one different norm under which this is like an optimal compression of this matrix. So that's the idea of low rank, through the SVD. So now let's take this really powerful tool that you can always apply to any matrix and gives you all these nice properties of like a controlled compression, and let's apply it to a tensor. All right, but how are we going to do that, right? Because it's not a matrix. It doesn't have 2 indices. In this case, it has 4 indices. So what can we do, right? So one thing we can do is we can just shoehorn it into being a matrix. We can say, let's arbitrarily divide off the first index from the other 3, and then let's reshape this thing as a matrix. And let me be really clear about what does that mean? What does reshaping mean here? It means that I have a matrix that's going to be very rectangular, where I have an entry like M11, where I set the row to 1, and I set all the column indices to 1. Then M12 is where I keep the row to 1, but now I tick to the next setting of the column indices. So basically, I use some kind of binary counting rule to just come up with some way of ordering all the different states that the column indices can be. And it's not so important what that ordering is. All that'll do is change the V that I get. And so I just tick through all these different settings of this collection of column indices. And that is how I can think of it as a matrix M. It's basically just like the reshape command in NumPy. That's really all I'm talking about. And then I throw that into the SVD, and I get a U, an S, and a V. So I can do that. But that was not a very tensor thing to do. I just forced it into being a matrix, right? Why didn't I could have done this. I could have partitioned it there and split and made these the row indices and these the column indices, okay? Or I could have done this one, right? So in general, well, first of all, let me say that from now on, when I talk about an SVD of a tensor, let me leave out this sort of tedious step of saying that I'm going to reshape it to a matrix. Let me just always know that that's what that means when I draw this line. And I'll just jump straight from here to this form, where U is no longer a matrix, but it's a tensor that I got from folding into a matrix and folding back. That's the idea. Okay, so I can just talk about this in an implicit way, SVDing a tensor. So that's what we want to do. Now let's think about a really big tensor, a tensor with a lot of indices, and think about all the different choices that we have. So we could cut here or partition here and say, okay, let's reshape this thing into, let's take all these indices to be dimension 2. I could think about reshaping into a 2 by 2 to the n minus 1 matrix and SVDing, or a 2 to the 2 by 2 to the n minus 2 matrix and SVD, and so on and so on. So I can slide this partition along, and I can get all these different SVDs. Okay, and so that's interesting, but shouldn't they be related in some way, because they all, in the end, if I put everything back together, still describe the same original tensor. And it turns out you can devise a format which is equivalent to having done all the SVDs at once simultaneously in a consistent way. And that's the matrix product state tensor network. That's really what's going on like inside a matrix product state tensor network. That's really what it is. This has another name in the math literature that you might see a lot called the tensor train. They're exactly the same thing, but just depending on the literature that you read, you'll see those 2 different names. Matrix product state is more commonly used in the physics literature. So you can think of it as a vast generalization of the SVD for tensors. Now, I didn't make a slide on this for the sake of time, but there's other generalizations of the SVD to tensors many of you may know. Like one of them is called the CP format. And these have different trade-offs. So the CP has the advantage of being symmetric. It treats all the indices on the same footing, whereas here, there's some ordering to the indices, as you can see. There's some index that's on the very left of this chain, and there's some index that's on the very right. So it's rather asymmetrical. But the MPS has some advantages too, like that you can always know you've computed the optimal MPS truncation in any given case. You give me a tensor and I'll just do these different SVDs, and I know that I can find the smallest bond dimension every time. But in the CP, you don't have that property. You may not actually find the most compressed CP, and it can be very hard to do so. So that's just a side comment for experts who know about that other decomposition. So now just a bit of perspective on what is going on here. One perspective that I was using on those previous slides was to view this network of tensors that's all summed together on these internal indices as coming from having SVD'd a big tensor a bunch of different ways. But we can also just view it the other way around. We can just view this network as defining like a manifold of tensors or a subspace of tensors that are low rank. We can just think of it that way. We can say, this is a tensor just as much as that is. It's just that this is a special family of tensors that's a subset of these. So we can just think of it that way too.
Sorry, Maz, I have one more question. This matrix products, this depends on the ordering of the indices, right?
Mm-hmm. That's right. So if you chose a different ordering, you might get a worse compression. Mm-hmm.
So
or better compression.
What if there's no canonical ordering? How do you know what the right ordering is for a given tensor?
Yeah, it's a great question. So in general, you don't, but in a lot of applications, there's like a natural ordering. So where these have had a lot of success in physics is in one-dimensional systems where there's some kind of natural, there's a clear order from the outset that makes sense. It's similar. I think there was a question at the end of Jason's talk yesterday about this too. Like, how do you know the order for a hierarchical matrix if it's just in some jumbled up form when it's given to you? I think it's a similar issue. In fact, I'm pretty sure that MPS are hierarchical matrices in a sense, but in a tensor product space. So I think it's actually like intimately related to that topic.
This also looks a bit like a hidden Markov model with all these matrices multiplied together.
Yeah, that's right. So they're very, very closely related to hidden Markov models. I think the difference is mostly a matter of like culture of that field in some sense. Correct me if I'm wrong, but I think with hidden Markov models, usually there's a little bit of additional constraints that are taken, like the entries have to be non-negative, and there's an interpretation taken that it's describing a probability distribution.
Right.
And so a lot of the MPS, and especially the tensor train literature, is like saying, let's relax those constraints and let's put in complex numbers, and it doesn't have to represent a probability distribution. And so it's sort of just relaxing away from some of those constraints.
So what's the dimensionality of those bars that go between the circles?
Yes, that's actually the main hyperparameter that you can adjust or can discover from the tensor. So let me come to that.
That's
really
not defined
briefly,
by the SVD that you just did?
That's right. So if you can afford to like instantiate or have some way of having the original tensor may not be like an array of numbers. You may have it as a sum of low ranked tensors, or you may have it as in some other form that you can efficiently evaluate. Then you can feed that into an SVD algorithm in some efficient way, and you can actually like print out these MPS tensors. And then basically just by setting a threshold on the truncations, you'll discover the size of these indices.
So going back to like covariance and contravariance, does this SVD actually preserve that structure? Like because once I perform these operations where I'm like taking indices and I'm like squishing them into bigger matrices, am I ensuring that does that process like ensure that everything transforms accordingly?
It does. That's a great question. I think there's actually more work to do there in the field. A lot of this was first run through by physicists who are like sort of notoriously casual about that stuff, but I think there's like a lot more to be said about that. But basically, yes. So the idea is if you do this all with arrows correctly, then you can think of the arrows as flowing out of the singular values. And then when you push the singular values one way, the arrow that's left over will be left. If you push it the other way, it goes to the right. So if you do everything carefully, you find there are like these arrows flowing along the network. And then that raises a very interesting question that I'm not going to cover in this talk. It's too advanced, but there's like an arbitrariness to this flow. The flow can terminate on this tensor, but it could also terminate on that tensor. And this gets into the idea of gauges, which are like redundancy in the description. That's another thing that seems like a disadvantage of MPS over things like CP, which doesn't have that gauge redundancy or much more limited gauge redundancy, but it's actually a crucial advantage. You can use this gauge redundancy to do all kinds of interesting mathematics, and it's actually been used to classify all phases of matter in one dimension in physics. So it's actually a very deep topic.
It's really interesting. Thanks.
Thanks. These are great questions. Okay, so briefly, just why is it called a matrix product state? This is just because the original understanding early on in like kind of actually in the 80s in a few papers was that it's like a way of recovering tensor elements by multiplying a bunch of matrices together. So let's say I have this tensor and it's defined by this MPS or approximated by this MPS, then the idea is let me go recover the 0, 1, 1, 0, 1 entry of this tensor. So I set those indices temporarily to these fixed values. So those indices are gone because they're set. And now I'm just coloring the remaining tensors with these different colors to remember, which slice I got by setting those values. And now you can see that this is just a chain of vector matrix multiplication. So it's a vector, matrix, 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 vector. So then I just do those one at a time efficiently and get a scalar. So I can, with very small computational overhead, recover any of the any of the 2 to the n values of this tensor that I want that way. So that's why it's called matrix product state. But tensor train is actually a catchier name. I kind of like it better. All right, so someone asked about these bonds, these indices inside. These can actually vary in size, but just for simplicity, let's just call them a uniform size. It's often notated as chi or r, or there's other names depending on the literature. And the key thing to notice here is that if we can pull off an approximation of the original tensor or some representation of it for some modest chi, so if chi can be 2 or 10 or 100, but not 100,000, then this is a massive compression, because the amount of parameters you need to store the thing on the left without any structure would be d to the n. But on the right, it's n times d times chi squared. You just have to store a handful of these chi by chi matrices, and there's n of them in general. So that's it. So it's this, you go from this exponential cost to this very low polynomial cost in terms of memory. And another key point I wanted to make is that then there's all these different algorithms you can do once you're working in this compressed form. So once you're working with tensors in this MPS form, which is the sort of best understood tensor network, and I'll tell you about some others very briefly in a minute, but this is sort of the main tensor network I want to talk about. Then there's all these different algorithms that you can do, and this is only some of them. You can sum 2 MPS while keeping everything in a compressed form with like a low polynomial cost. Generally, all these algorithms scale as bond dimension cubed, and memory usage is bond dimension squared. And then you can adapt the bond dimension of the result. So it can grow if needed or even shrink in some cases, and it's all adaptive and you can control the error. You can also multiply tensor networks by other tensor networks. So you can have this matrix-like tensor network called the MPO, matrix product operator. And you can do this, this contraction efficiently and get the result. And there's actually something like 5 or 6 very interesting different algorithms to do this with different scaling characteristics. It's like a whole subject that's worth looking into. And then let me go through one of these algorithms in detail to see how these things are efficient. So let's compute the inner product of 2 different MPS, or it could be the same MPS with itself. So let's see how that goes. So this is the network we want to contract. We have this MPS on the top, this red one, and we have this blue one on the bottom. And these could be different in general. And let's say we want their inner product. So that's just summing over all their normally open indices with each other. The way you do this efficiently, right? Because this would not be efficient if we just did the sum, all the sums at once. It would just be this exponentially big sum. What you do is you first take these 2 tensors and contract them over their shared index here. And that results in this new tensor that I'm showing as this gray blob. Then next you contract that one with this one. So you do this contraction. So you're basically just summing over this line. And these 3 lines here, here, and here are just held open in that sum. That results in this tensor. Now we're going to contract these 2. So again, now we're summing over their shared indices. So this one and this one. This index is held open, that index is held open. So that's just another small sum that you do in the computer. And then you just keep doing this. And you can call this algorithm, sometimes people call this like the bubbling algorithm, because you're basically just moving this little bubble along and combining pairs of tensors together, going down the chain. And you keep going and bubbling. And then you get a scalar at the end once you get to the end of the chain. And if you work out the costs of every step, it scales as bond dimension cubed, if let's say they both have a similar bond dimension, and memory is bond dimension squared. So we can do algorithms like this very, very efficiently. This just takes like, a fraction of a second just to run through, even for rather large MPS to do this. So in fact, let's talk about some sizes. So if each MPS represents a tensor with 40 indices of dimension 2, which is a pretty modest MPS calculation, we can do thousands of indices and things like that, then this algorithm is computing the dot product of 2 vectors, if you want to think about them as vectors, that would have 1 trillion entries each. But because they're low rank, we can do this. And so if we take the rank to be 100, this takes about 10 milliseconds to do. So it can be done very quickly. And then, again, I'm talking about the MPS a lot, but there's other tensor networks too. And they have a whole literature about each one. There's even more that I'm not showing on this slide, with their own algorithms that are in some cases under very heavy development and various degrees of expressive power. So the MPS is the simplest one, and it has a tree-like structure if you know kind of how to look at it. But you can do other more balanced trees as well. And this has been discovered in different contexts called hierarchical Tucker or tree tensor network. And then there's also a 2D analog of a MPS called a PEPS, which is not a great name, but it's just the name that caught on. Another name would be tensor grid network or tensor network state. There's different names for that one. So this is the one that has a lot of algorithm research going on into it currently, and there's been a lot of developments even in the last year. So let me now turn to some applications of tensor networks in the remaining time. Just to show you how I think these are now finding really diverse uses outside of physics and inside of physics. So I think it's an exciting subject, and I hope that because we have some expertise on it here at Flatiron, that I could talk to some of you about projects that you're working on, or you could tell me about techniques that you think might be helpful for working with tensor networks too. So one of the applications that I've not been involved in, but I've just been watching, and I think it's really interesting, is compressing neural networks with tensor networks. So the idea is that you have some neural network that has, it's a deep neural network and has multiple layers. And let's say we want to take one of the layers to be really big, very wide. So then there's a trick you can do where you can just reshape or view that weight layer. If it's very big, let's say we just pad it out to be a power of 2 in terms of its linear size. So we just choose it to be size 2 to the n by 2 to the n, because a weight layer, after all, is like a big matrix. Then we can also view that same collection of numbers as a tensor with 2 n indices, each of dimension 2. That's the same amount of numbers. So we can always just sort of reshape this 2 to the n by 2 to the n huge matrix into this tensor with 2 n indices. That's just something you can do. It's just a way of looking at it. But then there's a tensor network factorization you can either discover or impose on that weight layer. Let's say we just impose it. So you don't actually work with this whole tensor. At the very beginning, you just start with this network, which is called an MPO network, and you just put that into the neural network. Then you make your code, your backpropagation code, to go backprop through these tensors and train with that put in instead of a full weight layer. And people who have investigated this have found that they only lose a tiny bit of performance, but they get huge compressions, like 80x compression over using a dense weight layer. So that's a nice subject, and there's been different. These are not the only 2 papers on it, but there's been a few. Another subject that
I don't understand why the traditional general linear map here involves very many degrees of freedom.
Oh yeah.
If there's m going to n nodes, then it's just an m by n matrix, right? Between the 2 layers. I'm just trying to figure out why. Yeah. Why
would it be so big?
Yeah. Why is it 2 to the n, not just n times m as the general linear map here?
Mm-hmm. Well, of course, here it is m times n if you just define, this is m and that's n, okay. And that's the idea. I mean, it doesn't have to be square. That's just something I put to make the slide a little simpler. But I think it's more the idea is that it doesn't have to be big, but it's just that this lets you take it to be big. So it lets you investigate very, very, very wide networks, but which happen to be low rank in this sense. So it lets you go to some interesting limit and see how they perform.
Okay.
So I can't totally tell you everything about this subject in terms of its goals, but I just know that people have done this, and it's sort of like approaching an interesting limit of neural networks that you couldn't do in a brute force way.
In mouse? May I ask a quick question? So is this 80 for speed up or compression, exponential compression or polynomial?
Mm-hmm. It's exponential compression, but it's also, though, maybe as Alex was touching on, it's exponential compression over a limit that people don't normally do. It's like a very, very wide layer. I mean, I say that, although now there is this whole topic of investigating these these sort of limits of infinitely wide layers connecting to Gaussian processes and this neural tangent kernel and all those sort of things. So maybe there may be a connection there, though I don't know. Yeah, that's sort of the idea of it, is that you get this exponential compression overtaking this dense tensor in a very large limit.
So you're replacing a layer that otherwise would be a convolutional layer, or like this seems like an image recognition task, right? So most of the layers are convolutional layers.
You can do convolutional layers too. These 2 works, I believe, don't do that, but there's other works that I think do. Yeah, I think this one researcher named is either Jean or John Kasavi, who has this library called Tensorly. I think he's done some papers, if I'm not wrong, about
Right.
Convolutional layers and doing compressions like this.
Yeah.
I think some of that's with Enema and Kumar and some people too.
Yeah.
Rose U there's also a work with Rose U I should have put on here, doing this for recurrent neural networks. Very similar sort of idea too with RNNs. Okay. So again, I'm not totally always sure what's totally the goal of that work, but I think it's just interesting that you can do it. And it could connect to some other topics about wide layers, I think. Okay, so then totally switching gears, just because this is just sort of a kind of a, greatest hits of tensor networks part of the talk. So each slide is going to be rather different. Another rather different use of tensor networks is actually one of the oldest uses of tensor networks, which is solving PDEs, partial differential equations with tensor networks. In particular, the main one I know about how to set up in a tensor network framework is the Schrödinger equation of quantum mechanics. So here you have a single derivative time on the function that you're trying to solve for, and then you have a differential operator that acts in space on these R variables on the right that has various forms. So which form you take defines the problem that you're studying. And then you can discretize both H and psi by say introducing a basis set or other ways. And then once you've discretized them, in very interesting cases, in fact, the cases that in some sense are like the most natural cases, the cases that have to do with low temperature quantum systems and things like that, which are, and most quantum systems that we encounter are low temperature, then those can be discretized and happen to be low rank in many cases. And then you can represent them by tensor networks and represent things like the right-hand side as this product and get a really big advantage on the problem. So this problem is an exponentially costly problem on its face. So this is one way to break through that exponential scaling. There's other ways too. And by using this technique, results have been obtained, like for example, the low temperature solution, the stationary lowest energy state called the ground state of thousands of real three-dimensional hydrogen atoms to extreme accuracy. So this is like just one example you can do with this technology. Now, again, switching gears totally, another very different thing you can do with tensor networks is you can set up these, things like graphical models, in some sense literally graphical models or other tensor networks. And you can pose the problem of I have a bunch of tensors that I want to all contract all together, and when I'm done contracting them, I get a scalar. So you can have some kind of regular network or these other types of networks. I think one of them might be one of these small world networks, if I'm not mistaken, and just these other various different kinds of graph structures, which would be very expensive to contract if you did them in some kind of naive way. And then there's various schemes to do this, which don't involve tensor networks, like belief propagation. So TAP is like a kind of sophisticated belief propagation type of algorithm. And you can see all of these different, there's another one that has to do with neural networks, this VAN and ConVAN, or these newer neural network based, I think auto-regressive based schemes to do this. They all recovered the exact value of this network to some good accuracy. But then this new method that's appeared in this recent paper gets extremely higher accuracy and is very fast. So in some of these cases, it contracts the whole network in just like a second or two. And I don't have time to discuss how it works, but it's a very great idea. It's very fascinating. You take each tensor and you basically blow it up into an MPS. So if you remember earlier in the talk, I showed how you can basically unroll a big tensor into an MPS. You do that to every tensor in the network. Then you have this more fine-grained network. Then there's this set of moves you can do that are designed to be pretty efficient with MPS. So you do these index swapping moves and these combination moves, and you just keep going through these moves in a kind of a greedy fashion. And here I'm showing blowing up one of the tensors into an MPS. And that's it. So it's just something you can do in like 2 pages of Python code and then get these pretty incredible results for these contracting these networks. And interestingly, Adam German at CCA had essentially the same idea, or very close to the same idea in another paper that's in Cypos. So we have an expert on this in CCA too. And so it's interesting to talk to Adam about this work and this area, and he has some other follow-up ideas. All right, another very different topic, I'll kind of make sure I'm okay on time, is using tensor networks as machine learning models. So not just using them inside machine learning models, but just replacing the whole model with a tensor network. So say, why does it have to be inside of a neural network? Couldn't it just be the whole model? And it can. This is a recent work just from this year showing how to use one of these two-dimensional tensor networks to perform image classification tasks. And it gets state-of-the-art results for MNIST, tying neural networks. But then more impressively, it actually gets, I think, like the second best result known or something for this fashion MNIST data set, which is a challenging image data set of clothing. And it has some interesting advantages, like I believe much fewer parameters than associated neural networks would. But it also has a very high cost to train. So it has some drawbacks too that still need some work. Another paper from this year that used tensor networks in a different format to do machine learning is this one called anomaly detection with tensor networks. And it uses this ability to view tensor networks in this geometrical form because they're these linear transformations in high dimensional spaces to develop a nice framework for anomaly detection. So that's where you're looking for outliers in a data set. And then got state-of-the-art results beating a number of other neural network approaches on a certain tabular or heterogeneous data task or a set of these tabular data tasks. I just wanted to mention very briefly, there's actually a symposium this Friday at City University at the Graduate Center about this topic, about using tensor networks to do machine learning. So just wanted to advertise that really fast. It includes those two works actually that I mentioned. And then I think this is the last application, yes. Last application I'll mention, but there's many more I could tell you, is computing high dimensional integrals with tensor networks. And this is what I have a small activity on for those, if we have time in the discussion. I'm not sure if we have time, but we can talk about it. Or I can just talk with some of you by email and send you some sample codes if you want. But the idea is, let's say we want to compute the integral of a certain function over this interval, some arbitrary interval in this d-dimensional space. Then a standard idea to do this is to discretize the problem. So you introduce some kind of quadrature where you select specially selected points indexed by these integers k that go over, 10 different values. And then you have to introduce these weights, which are some kind of tabulated numbers that you just look up on Wikipedia or something and then can put here. And this will give you a very good approximation of this integral. However, this is still an exponentially hard thing to do. You have to run over this sum over these d variables. So you have like 10 to the d different values you have to sum over. So you haven't really gained a whole lot. The trick you can do is you can actually optimize an MPS tensor network, a matrix product state, to approximate this discretized version of f. So as long as you can afford to evaluate f on these points, you can say collect samples and then use these samples in a training algorithm. And there's various ones that are very interesting to figure out what numbers to put in this MPS to get a close approximation to f. And if you succeed at this optimization, this is the most expensive and complicated part, which I won't have time to go into. If you succeed at figuring out the parameters to put to approximate f, then you can do this integral very quickly and very efficiently. So you just define these little small vectors of these weights, and then you just stick them on one at a time. And this part just takes a second, and it's exact. But this is the part that takes all the time and is sort of subtle to do. But then you could pull off this integral without having to say do any Monte Carlo or anything else. Okay, so those are all the applications I just wanted to highlight. But just to show you the kind of breadth of different things you can do with tensor networks. So lastly, let me just give a little quick introduction to the iTensor software. I think some of you have seen that before, but just to show one way of designing software to work with these kinds of concepts of tensors that have many indices and heterogeneous numbers of indices and this kind of thing. And the main thing I want you to see is that we designed this iTensor software to try to mimic the experience of drawing tensor diagrams when writing code, short of actually having a graphical interface. So when you're working with tensor network algorithms, the thing you really are doing a lot of the time is tensor contraction. So summing over some shared indices between pairs of tensors. That takes up most of the conceptual steps in terms of what the algorithm is actually doing and whether you're doing the right thing or the wrong thing, as well as most of the computational time too is in these tensor contractions. And again, we don't really prefer to think about it in this kind of notation where you're sort of hunting for indices and you're having to spend, brain cycles remembering that J is the second index of this one and also the second index of that one. We'd rather just draw these pictures and just know the important thing here is that there's some index J shared between these two that we want to sum over and get that one. That's really all we want to do. And what can go wrong in this traditional approach? We might contract the wrong index. What if all the indices are the same size, right? So we may say, well, they're all dimension 2. Any of them can be contracted. So we might get them mixed up. We might spend too much time inputting the contractions, having to come up with names for all the indices and put the ordering, and that kind of thing. Also, it may take too long to actually do the computation. So if we can give some of it over to the computer, maybe it can do some optimizations for us. So in a conventional tensor library, not iTensor, so if you're using, say, NumPy and INSUM, then there's various interfaces, but a very typical one is that you temporarily introduce names of indices, and you are doing this to associate these names to the index ordering that you know. So you know that I is the first one, J is the second one, and K and L, and so on. And then you're just putting these labels in temporarily for the purpose of this one line. And then you're using this Einstein summation to say, well, K appears twice, so that is summed over, and L appears twice, so that's summed over. But this is just a temporary construction, and you have to know the ordering. You can make mistakes doing this. So the idea with iTensor is that these labels aren't temporary, but they're permanent. They live on the indices, and they're made for you. So you don't have to come up with names for everything. You just make the indices. You can still put labels if you want to print things out and see the names of things, but you don't have to. Even if you don't put a name here, you leave it off. There's like an internal name. It's like a unique ID number that always gets generated for every index. And then you put indices in pairs onto different tensors so that later when you want to contract these tensors together, these indices would have these ID numbers. They just find each other for you and they contract themselves. So you basically just do a little bit of upfront work to define indices. But most of the indices you actually don't define yourself. They actually result from factorizations that you do. So they're kind of born throughout the calculation. You would think you would spend a lot of time doing this, but you actually barely do it all. Then you're just mostly pulling tensors apart and indices get born, and later you're putting them back together and indices die. So that's actually what a lot of the calculations look like. And when you're putting them back together, you don't have to think very much about it. You just know this one somehow was split apart from that one in an earlier stage and some indices resulted, and then I just put them back together and the indices are gone. So this rules out problems in programming like having to remember index ordering or contracting wrong indices. You just think about the network topology. That's the ideal. It's not always that perfect, but that's sort of the design goal that we are striving for. So it's like tensor diagrams. And in some cases, it's just really ideal. Like when you're adding iTensors, all you have to know is that they're compatible to be added in the sense that they have the same collection of indices, and you just add them, and it always succeeds. And it figures out the ordering for you. It just picks basically the ordering of A, and it permutes B if needed, and just adds them.
So what would a transpose mean then?
That's an interesting question. So the idea of a transpose, I think, is actually like not really a necessary idea. So it's sort of an artifact of notation, I think. So when you're working with these diagrams, you just don't have a transpose. It sort of becomes a question of which index do you attach something to. So if you have a square matrix or a square tensor, it just means that there's two indices that you could attach something to, and you just have to say which one.
Well, or a transpose, what would that be? I mean,
we just don't have a transpose. Yeah. Yeah, there's just no need for it. So, I mean, it's a great question, but because I thought about this for a while. I was like,
what do you mean there's no need for it? How do I distinguish multiplying A times A and A times A transpose? I mean,
yeah, so there is something like a transpose in the sense of if you have arrows on, let's say you have a matrix-like tensor, then the arrows will have a direction to them. And so you do need to attach a contravariant to a covariant index. But if those indices resulted from an earlier factorization, they will be the ones that will attach because this index will be born from a tensor factorization. So when you go to do it, you won't accidentally attach it to the wrong side. But then otherwise, there's no, you don't have to do any bookkeeping of whether the matrix is like this or like that. It can be either way. And the code, if at the last minute, if you're bringing the vector over, and the code realizes it should actually be over here, it'll just transpose it for you and just do it. Yeah. Okay, hope that answered the question. But it's an interesting thing.
It kind of blows my mind. So.
Okay, yeah, no, I mean, that occurred to me some years ago. I thought, wait, we don't talk about transposes, should we? And then I realized you don't have to with tensor diagrams, basically, or maybe we do, but we think of it a different way or something. But tensor diagrams don't have a left to right ordering. They're like planar, so there's no sense of something being to the left or to the right of something anyway. Yeah. Okay, and then just lastly, this one's just sort of a quick slide to say that sometimes you might, if you're following that logic of those rules, you might realize that this is a very greedy system to contract. Any indices that can be contracted will. So to prevent, sometimes you don't want that. So to prevent that from happening, you can add these like lightweight primes onto indices, and that sort of pries them open, and then they don't contract. So we have ways of dealing with cases like that we commonly do. So then just to update you on this software, since it's one of the major activities at CCQ, so it's this tensor library, it's this general purpose tensor library with this kind of unusual interface. And this year we finished porting it to the Julia programming language. So it was in C++, and we actually did an entire port. So there's like no part of this new code that is in C++, it's all in Julia, but we're getting comparable speeds actually. So that has paid off. And rapid development time similar to what you would see in Python, though I would say in some cases kind of nicer too because of the compositionality of Julia. And we have a new paper on the archive about iTensor in this new language. So if you have any questions about how that's gone, porting code to Julia or using Julia, we'd be happy to tell you about that and talk about that experience. And Matt Fishman is the associate data scientist who led that effort. So then to conclude, I think I kind of, getting into my 5 minutes, there's been some really good questions though. I just wanted to show there's a lot more I could say that, we didn't have time for. There's many optimization algorithms. You may have wondered at some point, how do you put the numbers into a tensor network? Like how do they get in there originally? There's many cases where the numbers can be put in by hand to say represent interesting StatMech models, like say a spin glass. You can just put them in by hand. Those of you who know about graphical models would understand that one. But then there's all these other ways of, say, optimizing a tensor network. For example, if I want to bring it to be close to some function that I can evaluate at points, then there's multiple interesting algorithms to do this. DMRG, which is a version of alternating these squares with adaptivity. This one called the density matrix algorithm that's very interesting. And there's this one called TT cross. Invariance of that one is very, very elegant algorithm too. Many other applications like simulating large quantum computers efficiently, large-scale PCA, branch and bound strategies to figure out low-energy configurations of spin glasses. Then there's all these interesting computational strategies too to actually contract the networks, like tensor renormalization group. It's like a local decimation and compression strategy. There's these ideas of using block sparse tensors, which we use very heavily in physics, and they have to do with symmetries that flow along the lines inside of a tensor network. That gets into that contravariant covariant structure and gauge transformations topic, which is it's a whole thing. So then concluding thoughts is that, historically, at least people in my field have thought of tensor networks as wave functions. But now this work on tensor trains is showing that that was too narrow. So I think with the benefit of hindsight, now I think we might even get in the future a bigger perspective on these. And we may see that these are either the right way or a right way of doing linear algebra in exponentially large spaces. So if you want to do linear transformations in these huge spaces, like spaces of size 2 to the n, where n is 1,000, then tensor networks may be an essential tool for doing that. Similar to how hierarchical matrices are an essential tool in their domain too. I think they're very closely related. I put a point about that. I think there's still also very big developments yet to come in tensor networks if more people got to be working on it, like analogs of matrix factorizations that are deterministic and efficient. And they're probably still underused. There's many application domains that could be added to this list of interesting applications. And a lot of these applications could be pushed much further and much harder. So your area may be another area where these could be used. So let's talk about it. And thanks for your attention.